In this segment, we'll look at another small example, larger than the prior one though, of ARM assembly. And we'll have a lot of in-lecture questions here and in the future segments with only a few new concepts. We'll decipher and comment an assembly translation of this simple C program we'll look at, and that'll be in order to reinforce the ideas already presented so far. So, the program in question for our small example is prog5.c, right here. Take a minute to read and understand it. As you can see, it inputs 3 integers right here on the scanf, and then prints back the maximum of those 3, computes it and prints it. It calls max of 3 to do the computation, and then that function in turn calls, as you can see up here, max, which does a comparison of just 2 items to return their maximum. Much of the point of program 5.c is to generate a couple of stack frames, and that's why we have this odd function designed with max of 3 calling max. Now, supplied in the notes is prog5 from c.s, which has the result of a gcc-S command, like we discussed earlier. You might get a slightly different version if you run that command, remember, due to different GCC versions or other variations. Prog5 from c.s has the usual surfeit of assembly directives, which are going to be trimmed down to produce prog5.s, which we'll actually analyze, as here in the notes. Now, let's start with the max of 3 function, which is down a little ways here. Like range sum from prog4.s, this function starts by building its stack frame, but it uses a new assembly directive to do that. In prog4.s, range sum pushed fp and lr onto the stack via 2 store instructions, as you may recall. These 2, in fact. But max of 3 uses the single instruction stmfd, stimfd I suppose, spbang, and then in curly braces fp and lr. And this pushes both fp and lr onto the stack, and it adjusts sp as it does so. Pushing one or more registers onto the runtime stack is such a common action, it's pretty much the start of every function call, that it's common for ISAs, not just ARM, but a lot of instruction languages, or machine languages, to have specialized instructions for it. The ARM instruction is stimfd. It takes a curly braced list of registers, which may include any or all of the 16 registers, and it pushes them onto the RTS, moving backward or upward in address as it grows the RTS upward. The bang after the SP makes SP decrease along with this process, just as it does for the earlier instructions we were using in prog4.s. The SP register ends up holding the address of the last thing pushed onto the stack, or in other words, pointing to the new top of stack. Stimfd pushes the registers in number order. In other words, it pushes R0 before R1, or LR R14 before PC R15. This happens no matter what order they appear in the braces. You can't change it by resequencing them. So always list the registers in ascending order of register number. The assembler will warn you if you don't. And then question 1. Does the line 29 instruction here do exactly the same thing as the 2 str instructions above? Now, my tone implies probably not exactly. No, it doesn't. And the reason is what we just said. It puts FP on the stack first, below the LR, which is second, because FP is register number 11 and LR is register number 14. The 2 STRs, by contrast, put them in the opposite order. Now, in the prior code example, we put FP above LR because it was easier to understand the code that way when we built the frame with LDR instructions. But the normal order is what is done by STMFD, with FP at the very bottom of the stack frame and LR just above it, as shown here. So all our stack frames from now on will follow this new order. So question 2, just to reinforce some ideas here, what if we did these 2 instructions then to reflect that new order? We'll do a store of FP first to SP and then do a -4 increment on SP. Remember that option when we do a store. And then likewise store an LR so that the LR would be above the FP. Does that then do the same thing as the line 29 here, stem FD instruction? And the answer is that these two instructions do push FP and LR onto the stack in ascending order, but they increment SP after each push. It's a post-increment instead of a pre-increment. So it's different, and it would in fact leave SP pointing above LR after storing LR. All our code examples assume that SP points to the top word of the RTS, not to the empty space above it. But an equally valid approach would be to always put point SP to the next empty space above the RTS. Then we'd want behavior like those two stir instructions here. A stack design in which the TOS pointer points to the top filled spot in the stack, like ours, is called a full stack. A stack design in which the TOS pointer points to the next empty spot is an empty stack. The ARM ISA offers a STMED instruction that works just like STMFD, but post-increments SP to implement an empty stack. STMFD stands for Store Multiple Full Descending, and STMED stands for Store Multiple Empty Descending. Another way to say the same thing is that STMED does the same thing as these two store instructions would do. Now both the STM, FD, and ED are descending, quote unquote, because the address in SP decreases as the stack is filled. The stack grows backward in memory. One might imagine yet another RTS design with addresses increasing as the stack grew. For that design, in full and empty variations, there are STMFA and STMEA instructions: store multiple full ascending, store multiple empty ascending. So all four variations, STMFD, ED, FA, and EA, produce the same basic machine language instruction. There are two option bits in it to produce either ascending or descending order and empty or full behavior. Did we really need four variations? Yes, as a matter of fact. These instructions reflect the importance of runtime stack design and the fact that every programming language has slightly different calling conventions. Recall the term calling convention from earlier. This includes how the RTS grows, the direction of RTS growth, and it includes full or empty behavior. So a good instruction set architecture accommodates all the likely variations. And then one more shorthand. Just in case all those options aren't enough, the use of STMFD with SP is so common across many languages that ARM provides a pseudo instruction. ARM assembly provides a pseudo instruction that's a bit shorter. As the line 29 comment here indicates, push FPLR is an abbreviation for stimfud SP bang FPLR. You can put as many registers in the curly braces as you like. Okay, the bottom of our new stack frame is the location at which the old FP was stored. The stack pointer is at the LR. So line 30 correctly changes FP to point to the bottom of the new stack frame. Question 3. Explain how adding 4 to SP gives us the address of the bottom of the frame. Well, the answer is that SP currently points to the location of the stored LR. So we must add 4 to SP in order to get a location one full word further down the stack, and that would be the location of the stored FP, the bottom of the stack. Line 31 subtracts 12 bytes, 3 words, 12 bytes from SP, as the diagram shows now, creating 3 additional words of space in the stack frame. Lines 32 through 34 then fill those words with the three parameters A, B, and C, which are of course passed in registers R0, R1, and R2, per the calling convention. And these appear in the stack as shown now in the diagram. And looking back at the C code to be sure we remember what those parameters were, these are the three that got stored in the stack at those locations. And so question 4, please. Rewrite lines 32 to 34 to use SP instead of FP. So answering that, what we'll want to do is store R0, the A value, first parameter, at SP plus 8, R1 at SP plus 4, and then R2 at just SP. So the appropriate changes look like this. Now, as we said in earlier examples, when FP is used, it isn't always used, the stack frame can be accessed either via FP or SP. But FP is preferred by the compiler because in some more complex cases, the SP may change a little bit during the function execution. And then a final question for you. Figure out for yourself, please, what lines 35 through 37 are doing. Explain each instruction exactly. The answer is that they're doing the first call of max, and I'll bring that back again in the C code here. They're doing this call right there. That would be done first before the outer call. And of course it's being passed A and B. So this instruction, FP minus 12, minus 4, 8, 12, is loading B into R1, and then of course the FP minus 8 is loading A into R0, so we're passing A and B as we should, and then the line 37 of course jumps to max. In the next segment we'll look at how max adds its own stack frame to the runtime stack.